Hello, this video is a short introduction to the topic of topological matter. Here we will look at the system called the SSH model. It's very simple, but here we can already see some topological things going on. So our system will consist of one-dimensional system of atoms, which we can think of as being placed on a ring. We have two types of atoms of type A and B, and they will be grouped in pairs, and we label each of the pairs by a natural number. So if we only have one, let's say we have only one electron, so that electron, so our Hilbert space will correspond to the span of these vectors, each one of them corresponds to our electron being localized in an atom. So n will be a natural number which goes from 1 to capital N. But since we consider this to be in a ring, so the system is periodic. And by the way, it's not only periodic but translationally invariant. So this periodicity will correspond, mathematically speaking, to this relation. So if we think of n plus 1 to be the same as 1. So if in our expressions we for some reason have capital N plus 1, well, that will mean 1. Now our electron, suppose it is in this atom A, it will have some probability given by this, which will depend on this hopping amplitude V, to jump to atom B. And this is symmetric, so if our electron is here, it will have exactly the same probability of jumping to atom A. And if we have an electron here, it will have a probability of jumping to the A of the next pair, which is given by W. So we have this hopping in between atoms of the same pair, and this hopping between atoms of, well, these different pairs. So this will correspond to this Hamiltonian. This is a tight binding Hamiltonian, and it's very simple, and we want to study this. We want to find its spectrum and so on. So since H is invariant and the translation is in N, there is a special basis which will actually be the basis of eigenvectors of this translation operator. But here we can think of this as simply being another basis labeled by this K, which takes these values. And notice that here I explicitly present the fact that we consider minus pi to be the same as pi. So yeah, this will be also have some periodicity. And the relation of this new basis with the original basis is given by these expressions. So this is like a Fourier series. And well, it turns out that the eigenvectors of this Hamiltonian will have this will look like this. So we just don't know yet what will CKA and CKB be, but we know that it will be something of this sort. And so we will write this Hamiltonian in this basis. So to do that, we simply substitute this expression, this relation here, and we look at what we get. So substituting, it's very straightforward to obtain this expression. which can be highly simplified by observing that here, so this guy here um, is actually, so we have this identity. Okay, so basically when we have this sum, if k prime and k are the same, this will be 0, so this will be 1, and we have, well, we sum 1 n times, well, it's obvious that we'll get this. But if these guys are different, this thing will be, well, something periodic, and it's always 0, so, well, the sum will be 0 anyway. And we have this relation. So substituting that in the previous expression, our Hamiltonian gets this form, which is much better actually than the original, because here now, although we have matrix elements mixed between states labeled by B and A, we only have matrix elements of of the same K, you see. So this is almost diagonalized. And to finish the diagonalization, and therefore to find its spectrum and eigenvectors, here we will actually only look at the energy spectrum. We again take a vector. We take a vector of this form as showed before, and well, we assume that this is an eigenvector, and it turns out it actually is. And solving this eigenvalue problem is exactly the same as solving this one, as you can see by plugging here the psi of k ket. And well, we will call this matrix hk, and we have one for each value of k, and remember there are n different values of k. And if we calculate its eigenvalues, we see that for each value of k we will have two different eigenvalues, which will be given by this expression. Well, actually, if this square root is 0, so if this guy is 0, for and for that value of, for some value of VW and K, so that in that case, for that value of K, we will only have one eigenvalue. But for all the others, for each K, we'll have two different eigenvalues. So we are actually interested in the case where we have many electrons in our system. So to do that, we first have to remember that the electron has spin 1/2, and therefore we have for each electron like two internal states, so two spin states. And again, we will remember that we have to remember that the electron obeys the Pauli exclusion principle, and that which means that we cannot have two electrons in the same quantum state. And now we assume that there is no interaction between electrons. There's no interaction between electrons, and each one of them will behave, so be subjected to the original Hamiltonian. And so in the original Hamiltonian, we had, as we saw, we had two capital N different eigenstates. Each one is labeled, so, and they are labeled for each value of k takes n different values, and for each value of k we have two different eigenstates, one with positive, well, or zero energy, and the other one with negative or zero energy. So if we put two n electrons, so by the way, now when I say n, I'm referring to the capital N. So when we have two n electrons in our system, um, and we look at the ground state, and again we know that they obey the Pauli exclusion principle. So our two n electrons will occupy the n states of the Hamiltonian, which have the lower energy. So those n states will correspond to the all the possible values of k. And remember that for each value of k we have two different um, eigenstates, and each one of them with a different energy. And we will only occupy the one with negative or zero energy. So if indeed we put two n electrons in our system, and now we take the limit of n goes to infinity, so these problems in condensed matter, they are supposed to model real world materials, and there we have tons of electrons, and atoms, and so we can consider n goes to infinity. And if we take this limit, k in turn will take values in what we call the Brillouin zone. So in this specific case, it will just be the interval from closed interval from minus pi to pi, and we consider that minus pi is the same as pi. And so again, we still have the same, although k now, so since k now takes a continuum of values in this circle, so this is actually a circle, since and this is important, since we take an interval and we identify its boundary, the points in the boundary. So this will now be a continuous function, and we can plot these graphs, and this is what we call the band structure. So remember that in all this problem, v and w are considered constants, but we can see how the problem changes when we change these constants. So for instance, if w equals to 0, so if we don't have hopping between pairs of atoms, we will get these values for the energy for each of the values of k. This is a very boring situation, and well, if v equals 0, we get the same thing. And well, if v and w are different than 0, but for instance w is smaller than v, we will end up with this, and which is similar to the case of w being bigger than v. Actually, as you can see from this expression, if you interchange v with w, the band structure will, so the energy, the spectrum will be the same. However, these two situations are not exactly the same, as we will see later. When w equals v, we get this band structure. So when v equals w, there is actually a point where the energy becomes 0, and that point will actually be k equals pi or minus pi. So it's the same point. Minus pi and pi are the same point. And here now you see, if here we, So if we have our two n electrons in this system, we will have one electron for each these values of k, and they will well, sorry, actually we'll have two electrons for each value of k, and we will have electrons occupying with these energies, so with these negative, or well, in this case, zero energies. And in this situation, if we increase by a very small amount, like arbitrarily small amount of energy of our system, our electrons can get excited to these states. So even if I just add a small amount of energy to my system, my electrons can now reorganize their value, the states that they occupy, and they can start occupying states of positive energy. And well, the total, so the sum of all the k's of my electrons will be different than before. And in this case, we say that our system is a conductor. But here, well, both here and here, the same thing does not happen, because for an electron to go from here to here, it has to have a finite amount of there's a finite amount of energy that I need to add to my system so that the electrons can jump from this state to this one. So they will not, if the energy is too small, nothing will happen. And so we call this a conductor. Now the big question is this. So let's say that for each value of these W and K and V, sorry, we have a certain state, so a certain state of matter, but of this system, and this will be considered equivalent if our states will be of matter will be considered equivalent if I can deform my system continuously onto the other one without becoming a different. So the question is, can I deform this system? So can I change the values of W and V continuously, so that my system goes from this situation of W smaller than V to this situation of W bigger than V, without ever the energy being zero? Well, we can already see that this cannot happen, because well, if I want to take W to be smaller than V and change it so that W becomes bigger than V, at some point I will have to have W bigger than V. B W equal to V. But there's a more geometrical way of looking at this. So to see that, remember that sigma x, so we have these two Pauli matrices, and which we can organize them in this vector of matrices. And again, we have our HK matrix, which is given by this and can be expressed in this form, so of an inner product of this vector, which I will explicitly, so which we know explicitly what it is, and this vector of matrices. And by looking at this, we can see that the energy of this guy being zero, so the eigenvalues of this guy having eigenvalues 0 is exactly the same as this vector being the 0 vector. So this H of V and W will be a map from S1 or our Brillouin zone to R2, and well, for we have a different map for each value, um, for each values of which pair of values of V and W, and if we fix the value of V and W and we look of what map we get this. And as you can easily see, this is the parameterization of the circle. Now this will be a circle with center V0 and the radius W. And if you plot this for different situations of the V and the relationship of V with W, if V is smaller than W, you'll see that the circle will enclose the origin. And the origin is very important here because it is where our bands, so our system will have energy, at least at one point, energy 0. And when V is bigger than W, our circle will not enclose the origin. And well, when V equals W, we have something like this, and it will touch the origin at one point, as we have seen in the graphs of the bands. And so from here, since we can only have our Hamiltonian will be described by these matrices HK, we see that if I go from the state where V is smaller than W, so from a system where V is smaller than W to one where V is bigger than W, that will correspond to a circle, a circle of like a family of circles continuously moving in this direction, and it will have to at some point touch the origin. There's no way to go around it. And so at some point we will have something like this, where we will have one point touching the origin, which will correspond to an insulator, or to a conductor, which will correspond to a conductor, and so this guy is topologically inequivalent to this one, because we cannot deform this by changing the values continuously of V and W into this without ever crossing the origin, and so without ever having a conducting state, or a gapless state as we call it. And so if we draw the phase diagram, we end up with this. So for each value of W and V, we have a different system, so to speak. And well, in this region we can deform the values of these two parameters, of these two hopping amplitudes, and never have a conduct, so, and never having and all of the points we go through are insulators. And here the same thing, but we cannot go from here to here because well, we will have to cross this line at some point, and when we do so, we have a conductor state. So we say that these two regions of this parameter space correspond to two different topological phases of matter. And why topological? Well, because the reason why I cannot transform this circle into this continuously without crossing the origin is a matter of topology. So this was a short introduction the SSH model. There's still a lot that can be said, and the same things can be said in a more precise way. But this is just a first approach to get an idea and a feeling of what people deal with when it comes to topological matter, more specifically topological insulators.